So in this lecture, we will study how to fine tune a existing diffusion model. In last lecture, we saw how to use a pre-trained pipeline. Here we will fine tune it. Okay. So chapter is fine tuning. So this I've split in a different way than the Hugging Face course has because I think it makes a lot more sense. You can find the code on my GitHub repository. So if you go to my GitHub profile, there is Hugging Face image generation course, and in that thing, you have the two dash fine tuning the model. This is the codes file. Okay, so you can find code and run this one. So let's go into the code and we'll see how to fine tune. So these things we already know, importing all the essential packages. So that's fine, get it installed. Then what we are doing is we are using a existing pipeline whose name is, it's a pipeline given by Google company. It's a image generation diffusion model which generates celebrities, Hollywood celebrities, not Indian celebrities. Okay. And the image generated is 256 by 256 pixel. So if you take a look at this, you can see through words and deconstruct what it is doing. They have other pipelines like, cat generation or dog generation or something like that, but they all follow similar format and you know what they do. So get existing pipeline and get existing scheduler, and we are ready to start fine tuning. Now, before we do fine tuning, we need to understand why fine tune. I gave the example that this data set generates celebrities of USA only. And let's say you want to generate images of different country. You know, we want to generate Bollywood images, Hollywood images, Tollywood images, or anything else. So then we need to add on the existing knowledge. So that is fine tuning. Fine tuning is by leveraging the pre-trained model of a big company, which already has the knowledge we want, but the base course knowledge, by refining it on a specific problem with much less data set, we can get a high accuracy. So, solving these individual product related problems, fine tuning is the way to go, the most important step. For fine tuning, one common sense thing is it adds the knowledge on the starting data set. So, in celebrity faces, if I want to convert Hollywood celebrity faces to Bollywood celebrity faces, would that be a correct example? Think, and answer is no. Because there might be similar dressing. Oh, no, actually, answer is yes. the it learns the face structure and stuff. So with understanding the Hollywood celebrity knowledge, I think it should be able to fine tune for Bollywood ones. This example though is even better. We start with celebrity faces, Hollywood only, and the end data set is anime faces. So you see, we can now fine tune the celebrity faces, but to get into format of anime. So this is how fine tuning works. So what do? We have image generation pipeline and we have scheduler. These are the standard sentences in diffuser's model, right? I've given the dataset model, and these are the standard pre-processing things, the PyTorch code for it. You will find that this code is extremely standard. Learn to tune it out, learn to focus on only the essential stuff, and those lines are very few. So get these right, and rest is, quite easy. You can have a code snippet which you can reuse whenever you want. So you do this, pre-process the data, and then, like in the previous code, if you want to go inside a model which is part of this pipeline, so this pipeline, if you wanna find out what kind of models does it have, you will find it's very interesting. By executing one simple command, you can get the details. The command is vars of the variable you want think of, and then on top of that you say keys. Okay, so vars gives you a dictionary, and the dictionaries, we only want the keys, which columns, and here you will find it has two, unit and scheduler. So the model this pipeline uses is actually image generation pipeline dot unit. So in fine tuning, what we do is we get data batch by batch. Then we send it to the model. So model is part of here. You'll find image generation pipeline dot unit. This is the model here, right here. How does diffusion model work? In last lecture, I used a sculpting analogy. Sculptor removes the unnecessary part from the image, from the rock block, and eventually the sculpture we want remains. Similarly, here we start with a noisy image and we are in step by step removing noise iteratively. So at the final stages, we are removing only fine tuning small things. And in initial stages, we can remove noise in chunks. And this unit model is removes that noise. So what we do is we start with the noise, we remove the noise, keep removing until we get the image we want. And this is the training. So we do the noise prediction. We compare that noise prediction with the noise we ourselves added, the scheduler with which we add. So we compare the noise predicted with the actual noise and we minimize the model's parameters so that this is minimum. So when we are able to predict the noise correctly, we are also able to remove the noise to get the image we want. Okay, so this is how fine tuning works. So start with a random image and we keep going through this, and on a trained model, we get answers in the format we want. So here, I tried to get run this model on GPU and there were some problems. One, the I got a GPU, but storage was not enough. Here on my local PC, training time is slow. So that makes you realize, even though the code looks small, the majority of work goes into the training time. We are learning the parameters in such a brute force way that we forget how intense, resource intensive these trainings are. So, this running it on a different PC made me realize that, and I hope we don't forget it. When we are running it on, millions of, we think that we'll get millions of GPU. No, we can't. They're very expensive, and we are limited by the size of the GPU available to us. So that's why fine tuning is very important. Fine tuning allows us to use existing pipelines, existing models by big companies like Google, Facebook, Amazon. So here, if you check whatever the pipeline, so for example, it was, let's say, image generation. Here, celebrity or stable diffusion, like a mid journey, you give text and you get an output. So this model would have taken, a lot of money to fine tune and train. It is directly available. There is a model called by OpenAI. It's OpenAI's model. It kind of like has a textual understanding of millions of images on internet. OpenAI company did that, and it is made available to us to use, to build on top of it. That's why we do fine tuning. So spend time here, understand the importance of fine tuning, and see how with these very small functions and code snippets, we can fine tune the stuff to our requirement. So this is the theory part of it. This is another example wherein we start with data set of bedrooms and we fine tune it on images found on wiki art. So bedrooms would be photos of the regular bedrooms we find, and we fine tune it on images. So is this relevant? And answer turns out to be yes. Different artists have their different styles. So this website is very nice. Okay, this data set is also very interesting. 256 good timeless artists and their arts is available here, mostly from 9th century to 21st century, and the distribution, if you check, majority of images start from 13th century. So this range, 13th century to 21st century, images start from 16 to 365. What we do in this code is convert this bedroom photo into a art style inspired by images based on found on this wiki art. So this fine tuning works. The starting bedroom thing and fine tuning it for images, this works. Another example of a successful fine tuning. Think of other projects. I will try to, generate a, Bollywood celebrity thing and a few more to actually apply this concept. And so should you, to understand this a lot deeper. Okay. So in next lecture, we will go further and we will try to go even further than fine tuning and have even more control on the output generated. So this is how diffusion models is incrementally gonna get complicated until we reach the highest thing, stable diffusion. Okay, so see you in the next lecture.